A water clock or a clepsydra is a timepiece in which time is measured by the regulated flow of liquid into or out from a vessel. Water clocks, along with sundials, are likely to be among the oldest time-measuring instruments. Where and when they were first invented is not known. Ancient Egyptians made the first water clock that has been physically documented, and their water clocks consisted of simple outflow tanks, where time was measured by how much water left the tank. Greeks considerably advanced the water clock by tackling the problem of diminishing flow. They introduced several types of the inflow clepsydra, one of which included the earliest feedback control system. Their water clocks were used to time orations at court, to time visits to brothels, and for physicians to measure pulses. China was the first to add an intermediate tank to their water clock, keeping the pressure in the outflow tank constant. China typically used a 4-tank water clock for maximum accuracy. Their water clocks were used for making measurements for astronomy and astrology. The pressure of water at a given depth is given by the equation P equals PO plus rho GH, where rho is the density of water, G is the acceleration due to gravity, H is the depth of the water, and PO is the pressure at the water's surface. In order to maintain a constant rate of flow into our final collection vessel, we decided we needed to keep our water flowing into the collection vessel at a constant pressure. To do this, we adopted a 3-vessel model in which the final vessel measures the passage of time by the accumulation of water. The water in the intermediate vessel is kept at a constant height, and the first vessel feeds water into the rest of the water clock. We kept the height of the water constant in the intermediate vessel by drilling a hole in it. We added an additional vessel to collect the water flowing through this drilled hole, so as not to make a mess. We utilize needle valves in our design to help control the rate of flow because they allow for slow and regular passage of water. We want our clock to be as accurate as possible, but our prediction is that it will be about 3 minutes off for each 30 minutes that we measure, so we'll have a 10% uncertainty rate. We're going to go through a series of measurements to test this uncertainty and see how our hypothesis holds up. These were our results. We think that the systematic error is because our valve froze and then thawed during astronomical observations, making the valve about 5 minutes off. So, I'm not really sure about this one girl. We let her into our group because we wanted diversity points, but I'm pretty sure she doesn't even speak English.
Being the only visible minority here is kind of weird because sometimes they forget my name and they call me like dim sum or chopstick instead of my real name.
Ping pong! Go to Kong, make dumpling.
Okay, Karen, okay.
Project's really great. I can't think of a better way to spend a Saturday morning. You know, I love spending time with 4 sophomores. It was good.
So it's about 6:20. It's really cold out. Our clock's working, I think. I hope. Everything else is running pretty smoothly. Except I don't really like anyone in my group.
I think this project was really good for me. I do like to build. I like to build. And also I think I was really good for this project. How I had swipe access and ID codes to get to all the places and fetch the water and drill the holes and saw